Welcome back to Cloud 42. I'm James. We are still working on the servo drivetrain for the surface grinder automation project. In previous videos, we've assembled the X and Z axes and seen them move under their own power. And since we all live in three-dimensional meat space, that leaves the Y axis. Let's get to work. As I mentioned in the last video on the grinder project, all three axes on this machine are a little bit different, so the parts we need to make for the Y-axis are different from the parts we made for the X and Z axes. Now last time there was some discussion in the comments about the naming of the axes on this machine. I'm calling the left and right motion of the table X, the in and out motion of the saddle towards and away from the operator Z, and the vertical motion of the head Y. And that's because I'm using the pedantic definitions where the Z-axis is parallel to the rotation axis of the spindle. And since the spindle is pointing directly at the operator, that means that the Z-axis is the saddle moving in and out. X is left and right. That leaves Y for the vertical motion of the head. Now, different people do call these axes differently. You see this most often on a lathe. On a lathe, technically, the long axis along the bed of the lathe is parallel to the spindle. So that should be called Z. However, if you go out and look at lathe DROs that you can buy, sometimes it's labeled Z, sometimes it's labeled X. So for the people who pointed out in the comments that Curtis at Cutting Edge Engineering recently put a DRO on his lathe and he called the long axis Y, well, that's because he was using an Eason universal DRO that can be used on any machine, and they labeled the axes X and Y. So on his machine, it's Y. If you want to be pedantic, it's probably Z, but that's not going to do you any good if the button on the DRO says Y. So call it what you like. I'm going to call it what I like, and the Y-axis that we're going to work on today is the vertical motion of the head. If I pull off the belt cover here, we can see a little bit of what's going on, and we previously had this plate laser cut out of aluminum, mounted the motor, and now we need to work on the pulleys. I'm going to turn off the mesh of the model here so that we can see a little bit better what's going on. And if I bring this up in cross section, this is the clamp that holds the bearing in the top of the grinder. If I turn this back on briefly, that's actually inside this spigot that comes out the side of the grinder, and that shaft goes into the mechanism that raises and lowers the head. And this clamp reaches in and clamps the ball bearing in place. The shaft comes out, and you can see there is a section of the shaft that is recessed slightly. That's so that a set screw can bear on it without raising burrs that are then going to interfere with the pulley coming on and off, or in the case of the original machine, the hand wheel. And what we're going to make is we're going to make a cylindrical adapter that goes over the shaft, goes all the way in and bears against the inside bearing race, and then provides a surface that we can attach the pulley to. Now we could have just bored the pulley to match this shaft. The problem is that only one side of that pulley would bear on the full diameter of the shaft, and the side over here with the set screws would be over this gap. And that would probably work if the fit was really close, but those set screws are going to try to push the pulley off center, and since the edge of the pulley can move into that gap, it's not going to stay straight. So I would like to have this adapter bridge all the way over that, and we might as well go all the way to the bearing race just like the original hand wheel. Now, I don't believe we actually need pressure on this inner race to preload it like we did on the Z-axis, so this is really just to position the pulley and make it land in the right place. Now, if I turn off the cross section, you can see another problem that arises here, and that is that this is the original set screw that's actually in the aluminum pulley, and where it's positioned, that is behind the aluminum mounting plate, so there's actually no way to get a wrench on that. So what I need to do is add 2 more set screw holes to the pulley that are as close as I can get them to the pulley face, so that I can get in between this plate and the pulley with a wrench. So that's an M5 screw, and based on all the math that I've done and looking at these diagrams and looking at the model, I think I can get the wrench in there. I think it's going to be a lot tighter on the machine than it looks on the CAD model because, you know, keep in mind, we're zoomed way in on the CAD model. But I think that's going to work. And what I want to do is go ahead and run that screw through the pulley and through the steel adapter shaft That way we have the strength of the threads in the steel, but we have the additional length of having that aluminum. And I don't want to try to mess around with the original holes. I just want to drill new holes after I assemble the pulley to the adapter. I put together a drawing that I can use out in the shop. Just like last time, we need to bore the pulley out to 20 millimeters, but the adapter this time is a little bit different. It is just a straight cylinder with a bore through it, and the bore is a little bit long. 54 millimeters on a bore that narrow is going to be a little bit complicated to do on a small lathe, so I think I'll probably bore it till it's close and then ream it. And then I've got the threaded holes here shown in both the adapter and in the pulley. In reality, we're going to combine those and just drill through both parts, but I've got them dimensioned in both places so that I can take the dimensions off of either part when I'm in the shop actually making it. Just like last time, we need to bore this large pulley out to 20 millimeters. So just like last time, I'm going to mount it in the lathe, give it a little twist to try to make sure it's seated squarely. And then just like last time, we'll use a dial test indicator and get it running true. With that done, we can start boring, and I really like this little high-speed steel boring bar because it's really easy to start in small holes. The main limitation of it is, especially if you're cutting in steel, there's a lot of pressure, so there's a lot of flex, but in aluminum it does pretty well, as long as you don't need to bore any deeper than it will reach. So this is kind of about the limit of what that little bar will do. I'm going to eventually check this with a 3-point internal mic, but I'm going to start measuring with the calipers just because I would have to go through a bunch of different sizes of the 3-point internal mics, and it's easier to just use the calipers until we get close. I am doing the cutting here with some A9 lubricant. It's not really necessary, but it helps keep the aluminum from building up on the edge of the tool, and so I don't have to hone it as often. Now that we're getting close, we can pull out the 3-point internal mic and get a measurement. And I'm not just going to take a single measurement. I'm going to kind of fish around here in the bore a little bit just to make sure that we don't have some taper, make sure I'm not catching a burr. There are some screw holes in there. And I'll just take the measurement from multiple positions in the bore just to make sure that what I have is really representative. I set that into the DRO, and now I'm taking a final pass to bring it hopefully exactly to size. And taking a fine cut in aluminum with the A9 lubricant with this tool does leave a very nice surface finish. Get all the way through, pull it off the surface before we extract it just to make sure we don't leave a spiral groove in there, and then measure with the 3-point mic to see what dimension we hit. You'll remember last time I hit 20 millimeters right on the nose. What did we hit this time? Checking a few places just to make sure that the measurement I'm getting is representative and we don't have any kind of taper. And that's real close. I will take it. That part's done. Just need to deburr it. And this should be ready to assemble onto the adapter. Speaking of the adapter, let's make the adapter. I've got a piece of 1144 steel in here, and nothing really special is required for this, but 1144 is easy to turn on small machines, so that's what I opted for. Now this part has to be turned all in one setup, so I need to make sure that I have enough sticking out. Give it a little spin to make sure I'm not going to hit anything, and start by facing off the end. This not only cleans up the end of the part, but it gives me a 0 that I can set in the DRO for dimensioning everything else on the part. And we'll come back and take an initial pass just to take the skin off of the outside of the stock. And then this will give us our initial diameter for measurement so we can calibrate the DRO. Now I'll just double check here with my scale again to make sure that I've turned enough that I'll be able to part this off with the parting blade in the clean turned outer diameter. Now right now I'm just roughing. Okay, that's set to bananas. Let's try again with millimeters. I'm just roughing right now, so calipers will be fine to get an outside dimension, and set that in the DRO, and then I'll just start turning and work down to my desired outside dimension, I'll stay about a 0.5 millimeter shy of where I'm headed just because the part is going to be hot. I'm going to want to let it cool, and then I'm going to want to finish it up later. Stop the power feed and hand feed up to the shoulder. And now let's go ahead and put the hole through it. Now I'm not measuring at this point on the outside because again, the part is really hot. I need to let it cool before I can actually get a dimension and bring it to a fine final dimension. And the drilling is going to heat this thing up as well, so we'll just go ahead and get the bulk shape of this roughed out. I'm starting here with a 120-degree spotting drill, and I'm feeling the drill body just to see if there's any oscillation, see if it's moving because it started off center. And this feels pretty good, so I will go ahead and push it in deeper than I would normally push in a spotting drill, because I'm going to switch over to a jobber length drill held in a collet holder in the tool post. And then we'll go ahead and push this hole all the way through. And I want to make sure that I have a good deep hole to get this drill started in the right direction, make sure it can't wander. We'll give this a little lubricant, a little speed, and we'll just push this through. Now, this is a relatively small drill for the depth of hole I need to make here, so I'll be pulling it out and brushing off the chips periodically. Now technically I could just engage the power feed on the carriage and feed this through. But with this small of a drill, I don't really want to do that, especially when it gets deep, because I'm actually past the flutes. So I have to drill and then pull the drill out to clear them. This works. I'll get it through to depth. And then once it breaks through, I'll switch to a larger drill and start bringing the hole out to just under the size for the reamer. Do this in a couple of steps. This is around 3/8. I'm not actually using the 3/8 drill because I don't want to wear that. I'm using one of the drills close to that size, and now I'm up to a size 1 under the 12 millimeter final dimension. I'll put some air and some mist coolant on here just to cool down the part because it got quite hot from all of those operations. And once we get it down to room temperature or even a little bit colder than room temperature, we can bring it to the final size. Now for the bore, I actually have a 12 millimeter reamer, so this is what I'm going to use. If the bore were bigger or if it were not as deep, I would probably bore it with a boring bar first just to make sure it was absolutely concentric. But I don't have a boring bar that can go all the way through this that has the rigidity that I would want to be able to make a good cut. So I just got the drills as centered as I could. Ran the reamer through, and this will have to be good enough. I'm checking the internal diameter at several points. With a reamer, there shouldn't be any taper, but I'm just double checking to make sure the part's good. And that came out just over 12 millimeters. I think it's possible to get the reamer to cut a little bit smaller if I used like soluble oil instead of regular cutting oil, but that's probably a topic for another video. So I'll take one fine pass, about 1/4 millimeter off the outside, take a measurement, put that in my DRO, and then go to the final dimension and take a pass to actually bring this to the target dimension. Now I'm targeting slightly under 20 millimeters, so it'll be a slip fit in the pulley. And that looks about right. Looks like we're about 20 microns under. And you'll remember that the pulley was slightly over, so there should be plenty of room in here for a retaining compound, but it should still be a pretty nice slip fit. And that feels pretty good. Yeah, I'm going to call that good. And there's not appreciable taper here at all, so we can put the pulley on either end when we're done. Just feel the end of the part with a scale to line up the parting tool, then use the DRO to bring it down to the correct length measurement, and I'm just going to part this directly to length. Got a piece of welding rod in the tailstock chuck to catch the part. We'll spin this up nice and fast and just part it off. And as you've seen me do in previous videos, I'll bring it in, just touch the part, and as soon as it hits and starts to make a chip, I'll just start cranking and we'll push it through. And you can see the chips in this 1144 break beautifully with the parting tool. Just flip it around in the chuck and use a chamfer tool to put some tiny chamfers or just deburr the edges. And that part's done. Just like we did with the other adapter, we're going to assemble this with Loctite 609. This is a retaining compound intended for slip fits, and we should have just enough clearance in here to make this a really nice, solid connection. Now I want this to be lined up with the face of the pulley, so I'm going to clamp on a small parallel just to make it easy to line up so I don't have to do any measuring and I don't have to do any adjusting. And I'll just clamp this on with a couple of can't twist clamps, which has the added advantage of adding comedy to the YouTube video. I don't know if you've ever tried to handle one of these one-handed, but it can be pretty challenging. Okay, with those on, slide that down, make sure that registers, and it does. So now we can just add the retaining compound and glue this in. Now I've already wiped both of these parts down with 99% isopropyl alcohol, just to make sure there's no residual cutting oil on the surfaces and give the retaining compound the best chance of grabbing. Now, I don't know if there's a right way and a wrong way of doing this, but if there is a wrong way, you're probably looking at it. I'm sure you'll tell me all about that down in the comments, but I'm just going to put on a liberal amount, more than I need, and then rotate this as it goes in and kind of slide it back and forth to try to make sure that I've got a nice even coat of the compound over all of the mating surfaces. I can see a nice bead squeezed out on this side, and there's a nice bead squeezed out on the other side, so I'm pretty sure I've got this completely covered. And I'll go back through and just lock down these two set screws. We're not actually going to use these in the end, but since they're here, I'll use them to lock the parts together so that the retaining compound has a chance to set, and I can continue handling the part without risking breaking it free or misaligning it. Now I could leave the clamps on here, but if I do that, that parallel is going to become a permanent part of this assembly, and I definitely don't want that. So I'll take it off now that the set screws are locked to hold it together, and I'll wipe off the excess. Now this rag still has some alcohol on it from the cleanup, and so it makes short work of cleaning up the extra retaining compound. In fact, you won't even be able to tell the retaining compound is in there once this is all cleaned up. That looks great. Now this stuff will set up permanently in, a few hours. I think an hour or two. It should be well over 50% strength in this application. I don't remember. I read the data sheet and decided it was good enough and then didn't worry about it after that. But I'll probably let it sit overnight before I do any more machining on this. That's very satisfying. I don't know why, but simple things like this are just very satisfying. To put in the new set screw holes, we've got this mounted in a 5C collet block, and I've got it set up with the existing set screw holes at 90 degrees to the faces, so that the other two screw holes that we put in will be on the other 90-degree points around the circumference of the part. And as you've seen me do many times, I'll use an edge finder on the front and back jaws of the vise. Set the half function in the DRO to find the center line, and then I'll use the tip of the edge finder to find the inside surface of this pulley. Now this edge finder has a 4mm tip, so after I've got that zeroed, I'll move over 2mm and zero it again, and that'll give me my datum right on the edge of the pulley. Now this particular hole is for an M5 screw, and it's 2.6mm away from that pulley face, so it's very, very close. And there is no room for a spotting drill. So I'm going right to the tap drill size. I'm just starting it very carefully to make sure it doesn't wander, and then I'll push it through. You can see that part way down, those stringy chips turned to little crumbly chips, and that's because we've broken through from the aluminum into the steel. So about half of this screw is going to be in the aluminum, and about half of it will be in the 1144 steel adapter. Slow this down, put in the tap, and we'll just power tap it through. You can see the little blue mark on the tap that should come down to the top of the pulley, letting me know that I've got the full thread diameter through to the inside bore, but I haven't yet hit the other side and scrapped the part or broken the tap, or both. That looks good. Super close to the pulley face, but I don't see any marks on the face, so I think we did that correctly. Now I'll pull the collet block, rotate it 90 degrees, drop it back in, slide it over against the stop, so we don't have to recheck our datum, and then we can put in the other screw hole here 90 degrees away from the first one. will take the tap out before I mess around with anything else so I don't snap it off or jam it through the back of my hand. I do have a scar in my hand from a similar incident at one point in the past. And I don't do that anymore. I learned my lesson. And there are the screw holes. They're slightly out of focus, but I think they're going to work just fine. And now we get to find out if all that work done in the CAD model is going to pay off. Got the assembled adapter here. This is the shaft that it needs to go on. We'll slide that in. That screw hole you're looking at there is the original one in the pulley, and just like in the CAD model, it is not accessible when this is in position. And there's the new screw hole, and it looks like we're going to be able to reach that. I did do a corner-to-corner, calculation for the size of the hex wrench for these M5 screws and checked in the CAD model to make sure I could turn the wrench and it was going to clear that plate. And the CAD model said it would just clear the plate, and it looks like it will. We'll get the first one tightened down here a little bit, just so that I can have that bite into the shaft and I can rotate the shaft. Now we'll turn the second one down. And because I'm having to use the short handle of the wrench to turn this, I need to get something to apply a little bit of torque. Found a little T-handle wrench here with a hollow handle or a hollow shaft. And we'll give that a little bit of a turn. And then we'll tighten the other one just as well. So these are cup point screws, so they should bite into the shaft on that reduced diameter portion. I just want to make sure that that will actually happen. So I'm giving these about a quarter turn once they're tight. So it's actually winding up the wrench, between an eighth and a quarter of a turn of spring. And that looks great. And just like with the Z motor, I've bored out the small pulley to fit over the shaft, and I've got a dog point set screw that I'll put into the keyway. The usual caveats and disclaimers applies. It's probably not the best way to do it, but it's the way I chose to do it. And I've got the CAD model set up so that the pulley should be located with that dog point set screw all the way at the bottom of the keyway. Snug that down, put in the other screw, and then we'll put some torque on both of these to make sure they're biting in well and this isn't going to move at all on the shaft. If it does, it's going to reduce the accuracy of the machine, and it's ultimately going to wear on the shaft, and we definitely don't want that. When I put this together for the last time, I'll probably mark the pulley and the shaft with a paint pen just so I can make sure that over time it doesn't shift at all. Motor goes back on just the same way we put it on multiple times before, with these laser cut nut plates on the back and 4 M5 screws. I'll put these in loose initially with both of these nut plates on here so that the motor can slide up and down in those slots, and that'll give me the freedom to install the belt and adjust it for tension before I tighten everything down. And unlike the Z-axis, we have so much better access here that the belt just goes right over the pulleys with no trouble. I had to fumble with that down on the Z-axis just because there were so many things in the way. Put some pressure on this with my thumb and tighten it down and just see how we're doing. And that tension seems pretty good, so I'll just lock it in place. It's easy to come back and adjust it later. Put enough torque on these that they won't slip, they won't move. And that actually looks pretty good. I expected to have to fiddle with this for a little bit, but no, I think that tension's going to be fine. There's not a huge amount of torque right here because of the multiplication of force from the lead screw. So I think this is okay. If it's not, I can always come back and adjust it later. And then just as a sanity check, I will throw the dust cover or the belt guard over this. This is just a 3D printed part that I made. I don't think I showed this in a previous video. That's just polycarbonate with a laser etched logo. Now it looks great. With everything connected mechanically, we can tune the motor using the ClearPath software. I'll just leave the torque set to 100%, 1000 RPM maximum, and we do need to set the rotation limit so that it doesn't crash the machine. And that's pretty easy. We can just come in here and use the motor to actually rotate and move the machine through a range of motion. And you can see that bar graph on the right is telling us when we have given it enough rotation for it to do a good tuning. But I'm going to go ahead and give it all the rotations it wants. We might as well give it all 50. Let's speed through this. That's good. And now we can review our parameters and start the tuning process. Yeah, we know it might make some noises. Click run and it will start. Now you can see it's already moving back and forth very, very gently, and it's still moving now, but it's just moving a tiny, tiny bit. And as it moves through the tuning process, it will move faster and faster and more violently. And what it's doing is adjusting the parameters in the control loop in the servo to compensate for the mechanics of the machine, so that the servo is learning how to move the load rapidly and stop it at exactly the right point. It's figuring out the dynamics of the situation. As this goes along, it moves faster and faster. It goes through a whole bunch of different patterns. This process takes between 15 and maybe 30 minutes, depending on the machine and depending on what the motor's finding as it runs. In this case, I think it took about 15 minutes because this is a screw-driven axis on the machine, so it's really easy to tune. There's not a lot of inertia reflected back into the motor. At 95% here, just about done. And that's 100%. Tuning is complete. So I'll bring up the motion window and just drive the motor around a little bit and see how it's working. Seems to be working. That looks pretty smooth. Seems to have plenty of torque to raise or lower the head. So we'll set up a repeat profile here. Start with something really short, maybe 800 steps. That's one revolution of the motor itself. Set up some parameters for acceleration and dwell, and give it a try. That seems pretty well behaved. Let's ramp it up. I don't see any oscillation. I don't see anything funny. This looks pretty good. Let's go ahead and ramp this up and move it a full inch on the dial indicator here. Or close to it. That looks really good. Now, of course, the thing that really matters on a surface grinder, especially on the y-axis, is repeatability and accuracy. So I've got it set up here. It's moving back and forth about 0.004 of an inch. And I just want to see if it looks like it's repeating or if we are seeing some error. And at least with a thousandths indicator, this looks pretty good. But this is a surface grinder, so let me grab a 0.010 of an inch indicator. And let's take a little bit closer look and see how accurate it really is. Okay, this is a tenths indicator. It's got a much shorter range, of course. And I'll get this set up so we're moving back and forth exactly 0.005 of an inch. And just let this run for a minute and see. Now, of course, the downward motion where the needle goes and stops at 0 is the one that really matters, because that's the kind of move we'll be making when we set the height of the grinding wheel. And this looks really good. One division on this dial is 1/10,000th of an inch, and if there's any error here, it's just a tiny fraction of that. This looks really good. I think this is going to work great. I could not be happier with how that went. The y-axis is the most critical for the accuracy of the grinder, and seeing that we can hit the same position repeatedly within a micron or two just makes me smile. I'm honestly not sure I could do that with the hand wheels. As usual, the CAD model and drawings for this project are available on Patreon. If you like what I do here and want to support the channel, that's the best way to do it. I'll put a link in the video description. Thank you for watching.